I am going to basically continue with the capacitors. I intended to get through capacitors last class period. In fact, I said that at the beginning, but we didn't get to them, so we will today. So I believe we had this picture. I talked about the calculations, but I want to make sure that I'm really clear on just a couple of key ideas. Here is showing uniform electric field lines. The green lines are electric field lines. How do I know they're uniform? By looking at the picture. They're what? Okay, the spacing between them is all the same, which means that the strength is the same because the strength is inversely proportional to the separation, and the directions are all the same. So that tells me it's uniform. Now we know that work done by a force is the force dotted to the distance, the force times the distance parallel. So if I were to put a positive charge in here, so if I put a positive charge right here, then the force is QE vector, so the force would be in the direction of the electric field line. And if left to its own behavior, that force is going to make it then accelerate in the direction of the force. And so I would have it move under that force, and if it moves some distance d, then the work done is going to be the force QE times the distance, and since it's going to move parallel to the distance, the work would be QED. You remember me joking, usually that stands for quadrat demonstratum, sometimes quantum electrodynamics, but here it's just charge times electric field times distance. So that's going to be my work done by the electric field. That's only if I left it to its own devices. Obviously, if I held it so it couldn't move, how much work would the electric field do? If the distance it moves is 0, it's going to have 0 work done. And if, instead of moving parallel to the electric field, what if I moved it this direction? It'd be 0 because there's no distance parallel to the force. So there's no change in potential energy if you move perpendicular to the electric field lines. Thus we call motion perpendicular to electric field lines motion that is equipotential, equal potential. Remember, potential is just potential energy divided by charge. So this picture has marked electric potentials. Those lines of constant electric potential are called equipotential lines. And they have to be perpendicular to the electric field lines because they have to be the direction where if you move the charge, there's no work done by the electric field. Okay, moving on. We define change in potential energy as minus the work. So the change in electric potential is minus the electric work, so minus QED. And then finally, the electric potential is the electric potential energy change divided by charge. So minus QED over Q, or in the end, delta V is equal to minus ED. The minus sign has to do with the direction. If you're going parallel to the electric field, the voltage is dropping. That's why the minus sign means. So usually, we simply remember this equation as change in voltage is equal to ED, or V equals N, if you prefer. The change in voltage is electric field times distance, but you have to remember that is only if E is parallel to D and E is uniform. So this is a special equation. It only works in a uniform electric field if D is parallel to the electric field. Otherwise, what do you use? Well, you use something like, if it's a point charge, then you have V is equal to KQ over R, and you calculate the difference between the two R's. Not the R's themselves, but the V's for the two R's. Now, this slide I did show you because I want to introduce the unit of the electron volt. So the very simple problem that's illustrated here is I have two plates. And let's say that this plate is at, 1,000 volts, and this one is at 6,000 volts. They're both at positive voltages. What does that mean if they're both positive voltages? They're what? Not actually. The reason I ask this question is because we have to remember that voltage is based on potential energy, and potential energy has an arbitrary reference point. Right? Potential energy could be zero wherever you define it to be zero. So if they're both positive, it just means that they're both above where you define it to be zero. Same is true for voltage. If they're both positive, it just means they're both higher than where you define it to be zero. The only thing that really matters to us in working problems is the difference in those voltages. And so since it goes up by 5,000 volts, that means that a charge moving through it is going to have a change in potential energy that is its charge multiplied by that 5,000 volts. So if we look at this problem, we would have the electron starts, let's say we start with, does it say at rest? It does not. So we have to start by saying V initial is 0. And we say change in potential energy is equal to Q delta V. That's a definition, right? The definition of delta V, change in potential energy, is Q delta V. And work non-conservative equals 0 is equal to change in kinetic energy plus change in potential energy. Notice this line here is all from first semester. You can't do the second semester physics without the first semester physics, or you're just going to be off in Egypt. You're just straight up lost. So maybe I shouldn't use off in Egypt. Children of Israel were lost in Egypt, but I don't know. It might have different connotation to people. I've never thought about that. Just seeing the biblical reference was useful. Sorry for thinking when I'm teaching. Should never think when I'm teaching, right? Okay, so work non-conservative is change in kinetic energy plus change in potential energy. And my change in potential energy is Q delta V. So that means that I can solve this. Change in kinetic energy is equal to minus the change in potential energy, or, come on, 1/2 mass times V final squared minus 1/2 mass times V initial squared is equal to minus Q delta V. So now for this problem gave us specific values. It gave us delta V is equal to 5,000 volts. Is that a positive or a negative 5,000 volts? Going from the starting position shown to the ending position. Is it going up or down? Okay, Brittany says it's going up, and she's right. So I'm going to write the positive just so we're clear. The charge. What's the charge equal to here? It's an electron. What's the charge? It's negative E. So we have those two values, plus we had the initial velocity was 0, and the mass is equal to the mass of an electron. And so now I have everything I need to solve this for V final. First and foremost, V initial was 0. That makes life a lot easier. So V final squared is equal to multiply by 2 and divide by m minus 2q delta V over m. And then I have to square root it. Now, some people might look at this and say, oh no, you have the square root of a negative. What do you get if you have a square root of a negative? Imaginary. Can my electron have an imaginary speed? I'm going with no. One of the things that I have in quantum mechanics is your observables have to all be real. They can't be imaginary. So it has to be real. Well, will this be real? Was delta V positive? Yes. Was Q positive? No. So when I actually put in my values, minus 2 times minus E times delta V, the minus signs multiply together to give me a positive, and I have something that's just fine. It would be traveling at I put my square root sign first, and then I always go the wrong length. And so that gives me the final speed. And without doing the calculation, I can still see that it's going to be going pretty quick. Because, 10 to the minus 19 divided by 10 to the minus 31 is going to be 31 minus 19 is 12. And then times 5,000 times 2, so times, add another 4 zeros. 16, square root of 16 is 8. We're going somewhere close to the speed of light. Right, so it's going to be going really, really fast. 5,000 volts. Did somebody actually do this calculation?
4.19 times 10 to the 7.
Speed of light is 3 times 10 to the 8th meters per second. Our rule of thumb that we will learn in a month or so is that we have to treat a particle as relativistic if it's going greater than 10% the speed of light. It's already reached a relativistic velocity just by a 5,000 volt acceleration. So it's really cooking. And of course, what happened if you said 500,000 volts? You would get a speed as fast as the speed of light. Then well, that's clearly wrong. We have to use the relativistic calculation. We're not doing relativity right now, so we keep it down here. So that's how we can find, for instance, the kinetic energy of a particle when it goes through a voltage difference. Remember, we use the unit electron volts because I could say right away, just from these, the change in potential energy is equal to Q delta V is equal to minus E times 5,000 volts is equal to minus 5,000 electron volts. That's why we have this unit, because I don't have to pull out a calculator to do that calculation, which then allowed me to use this equation. I could have said, aha, the change in kinetic energy is plus 5,000 electron volts. And then I just go from that 5,000 electron volts to how many meters per second that's going to be for an electron. So a number of your homework problems have essentially the work that I just did. I made sure I worked out what an electron volt is for you, so you have that unit making sense. The rest of this, while it's very useful to see the actual application of stuff from last semester, it is all stuff that you've already learned. We just have to shake the rust off of it. So since I did them this morning with students, I know problem 1 and problem 3 are essentially this problem. Equipotential lines. I already defined equipotential lines in today's lecture. So you tell me, what did I define equipotential lines as? They're what? Okay, they were lines where there is no work done if you move along them, which means the potential energy is constant as you move along them, which means that the electric potential is constant as you move along them. Electric potential is constant is what equipotential means. So the equipotential lines, all of those things came from what Rebecca said. No work done as you move along them, hence constant potential energy, which means constant electric potential, and the name equipotential lines. I also said the equipotential lines have to be perpendicular to the electric field lines. So if you know what the electric field lines are, you can calculate what the equipotential lines are. You just draw the perpendiculars everywhere and connect your field. Or the other way around, if you know your electric potential, you can calculate what the electric field lines are by drawing the equipotential lines and then the perpendiculars. So two ways of looking at charge. One is looking at equipotential lines. And one is looking at electric field lines. One thing's really clear, different. Electric field lines have arrows. They have direction because they're vectors. Equipotential lines don't have arrows. There's no direction to them. The equipotential lines and electric field lines are always perpendicular because electric field lines always start or end at a charge or infinity far away. Then the equipotential lines can't ever go into a charge. They loop around them. And so if you look at the equipotential lines, you see loops around the charges, but not going into or out of the charges. Reading equipotential maps is exactly the same as reading a topographical map. Now, those of you in IRR class have probably had to, or if you haven't, you will have to, learn to read a topo map, a map that has the elevations marked. And when you look at equipotential lines, it's essentially the same. The elevation is equivalent to the electric potential because for gravitational force or gravitational potential energy, it's the elevation multiplied by mg. And for electric fields, the potential energy is the electric potential multiplied by the charge. So they have the same functionality. If I look at just this picture, the electric potentials are getting more and more negative as I get to these dots. What does that tell me about the sign of those dots, positive or negative? Go ahead. They're going to be negative because negative charge has lower electric potential, positive charge has higher electric potential. So because it goes -5, -10 as I approach, it's getting more negative, means I'm going toward a negative charge. It could have been 25-20. As long as it's going down, going more negative, it's going toward a negative charge. Because remember, the 0 point is fairly irrelevant. It's only the direction it's changing. Okay, clicker question. Please work. So far, it looks like it's actually going to work. We'll see. What is the relationship between equipotential lines and electric field lines? Jeffrey was first. And the first three people to answer all had different answers. And honestly, I don't know if you were right or wrong, any of you. So,
What's the class name again?
it's Web Fizz. Okay, waiting for Abby, Noah, Ashley, Brittany, and Michaela. Noah's answer. Oh, Abby's not here. I guess we'll wait a long time for her. So just waiting for Ashley. There we go. It deleted them, but I memorized them. 110.8. Okay, we do not have a consensus, although we do have a majority. Go ahead and turn to your neighbor and discuss what this should have been.
Yes.
Okay, have you guys come to consensus? Let's try again. Okay, it's open for answers, and yes, people are flooding in. We've got 12 responses already. No dice yet. Oh, there you go. Okay. So it moved toward the bottom one after people discussed it. Christian, discuss it with everyone.
Well, I don't know how to put it in words, but
Use hand signs.
electric field. I remembered how on the homework it's like related to the force of which like the charges are affecting it in a certain area. So I would see.
Okay, force is QE is the equation you're talking to. And so electric field lines show the force. That's right. And since this one here said energy, that was wrong. Good answer. Equipotential lines indicate energy because the potential energy is Q times the electric potential. The force is Q times the electric field. Don't break expensive $100 pen. So those were the relationships mathematically to go with what you said. Okay, good job. I'm just going to move past that one and go to another clicker question. Please work. Good chance you can answer now. An electron is placed between two vertical parallel plates held at minus 100 volts and 50 volts respectively. I'll draw a picture while you're answering. What will the electron do when you release it? Only people in the third line of answer. Okay, there Ashley broke the strand. Okay, Brittany and Corso. Not yet. You answered the last 2 times, though. Okay, there it goes. We had a last second defection from the B answers. Okay, Arlene, it's going straight to you.
I put D because they're both negative.
Okay, they're both negative. What's the rule on what the electron's going to go to? Okay, it's going to go, electrons are attracted to positive, repelled from negative, right? And so the more positive the voltage, the more positive the charge. So it would be minus 50 volts could be positive charge. You don't know because the reference point is undefined, right? It's anybody's choice. But you know that it's going to be repelled more from the minus 100 volts than it's repelled from minus 50 volts. So it's going to move toward the 50 volts, the minus 50 volts, excuse me. So you answered correctly, and your reason was there. It's going to go toward the more positive voltage. Even if it's still negative, it's going toward the more positive voltage. That was the point I was trying to get across here.
Can you explain from like a couple of slides above, you said that it would go like it would, this one right here,
Mhm.
it was going to get more negative because.
I said because the equipotential lines are getting more negative as you go toward the charges, that means those are negative charges. So if you go to this one here, 50 is less negative, minus 50 is less negative than minus 100. So minus 50 is more positive. And so the negative is going to go toward the more positive. Now, practical example. It used to be that everyone had a cathode ray tube. Nowadays, we all have these things. Flat panel displays that use something like a liquid crystal diode. So this isn't something that's so common for students to use anymore, but still a great application of just what we've been learning. So how does your traditional tube TV work? It's called a cathode ray tube, CRT for short. It's called a cathode ray because back at its discovery, they called the things coming out of the cathode ray. So what's the cathode? This part confuses me, especially because we're going to talk about batteries maybe at the end of today's lecture. And with the battery, the cathode is the positive terminal. But when we talk about the vacuum tube here, the cathode is the negative terminal. Hooray. A cathode ray tube, such as your traditional television, starts with that little filament. It's a wire, a tungsten wire. The reason I paid for the tungsten element on that periodic table upstairs is, well, it's because tungsten is W Wolfram. But I made my little statement, let your light so shine before men that they might see your good works and glorify your God who is in heaven, because we use tungsten for those filaments in our lights. So why do we use tungsten? It has a really high melting temperature. You put current through it. Current is something that I will introduce in lab tomorrow. In lab, I'm going to introduce current and talk about circuits, and then we're going to do a simple circuits experiment. Current is charge flowing through the wire. As charge flows through the wire, it makes the wire hot, and the hot wire starts emitting electrons. So it's basically blowing electrons off of that wire. So there's our first thing. The filament is just an electron source. So if we zoom in on that filament, we say, okay, the filament just has a bunch of electrons that are coming off. The voltage on that filament is only around 7 volts. So that means these electrons are going to have a maximum kinetic energy of about 7 electron volts. That's the maximum. But they're made inside this chamber that's held at a negative voltage. That voltage might be, let's say, minus 1,000 volts. And then the anode here is positive. We'll just connect that to ground. So they come out the little hole in the can, and they see ground, an electron negative charge. Ground is very positive compared to the negative 1,000 volts. So the electrons are accelerated across there. How much kinetic energy will the electrons have when they get to the anode? They go from minus 1,000 volts to 0 volts. What will their kinetic energy be? Let's suppose it starts with 0 kinetic energy for simplicity. If an electron goes across a 1,000 volt difference, how much does this kinetic energy change by? 1,000 electron volts. So it has the 1,000 electron volts, plus or minus 7 electron volts. That plus or minus is now a pretty small percentage of the total kinetic energy. So we just say, okay, it's fundamentally 1,000 electron volts. The uncertainty is a little bit less than 1%. So now these electrons are cooking. We can do the calculation like we did before and calculate the speed, right? It's going to be approximately a little less than 1/2 of what we found before. So it's going to be going somewhere in the ballpark of, let's say, 1.5 times 10 to the 7th meters per second. Still going very fast. And then we put through these plates. So one side is positive, one side's negative. If I have an electron going through there, what's the electron going to do when it goes between those plates? It's going to have a force taking it toward the positive side. So it's going to have a force like that. Because it's going very quickly, it's not in there very long, but there's going to be some work done because of the time it's in there. So it comes going straight, but then it gets deflected in the direction toward the positive away from the negative. So we adjust the voltages on that to make the electron beam go from the left side of the TV to the right side of the TV. So that plate is making the electron hit different portions of the screen left to right. And then we repeat that with a set of plates that are up and down. And so the electron is going to be swept up and down with the second set of plates. So you put those two plates together, and you're aiming where the electrons are going to hit the screen. So all you have to do then to adjust where the electrons hit the screen is you have voltage A and voltage B that you vary as a function of time. So voltage A is going left to right on the screen, and that voltage just goes like, okay, that should have been a straight down line. Nice. It's going to erase everything when I erase that one. It goes like this. So the ramp part is sweeping across the screen. And then this here is a dead time between one line and the next. So it's going. Now the VB is controlling the vertical. And so that one that just goes like this. So you do steps. And so the TV is actually making electrons go across the screen, shooting electrons at the screen. How does this do us any good for watching, MacGyver? MacGyver, like patron saint of all nerds, right? Anyone? Yeah. You have here a whole bunch of pixels. Pixel is short for picture cell. And those pixels have, okay, so black for my pixel. And in that pixel, there's a little blue dot, a little red dot, and a little green dot. What are those little dots? They're phosphors. Phosphors that are activated when electrons with the right energy hit them. And so this might be my green electron gun. The electron gun is only for one color. So a color TV has 3 of these, one for each color. And you have those little phosphors. When the electrons hit the phosphor, if it's the right energy electrons, that means you have to have different accelerating voltages for the different colors. Then it will absorb the energy of the electron and glow with the appropriate color. You have the 3 different phosphors, so you can respond to 3 different electron energies and get 3 different colors. Final thing is, of course, you need to adjust the brightness. The adjustment of the brightness is done with the filament. If you have more electrons, you're going to have more of the phosphor that's excited. It'll be brighter. And so they adjust the current on that filament for how bright they want the picture to be. Stronger current in the filament means you're going to make it so you have more electrons emitted and you make a brighter picture. So that's the way a traditional television works. It's a simple application of the things we've learned so far this semester. Now, I say simple. It's not really simple when you make a working one that has a pretty picture. You can make one with a really crummy picture and call it simple. But to make a really nice picture, you have to do some very careful things, collimating and focusing the beam. And yeah, it gets very complicated. But the ideas are simple. Now to capacitors, because I told you we'd get there. Capacitors are little devices that store energy in the form of an electric field. Now, that's an important thing. What does the capacitor do? Stores energy in the form of, now I gave you one of 2 options on the in the form of. I said in the form of an electric field. We think of these electric fields as force fields, and so we say that they store up energy. And with the work that we're going to do here with the capacitor, you can calculate how much energy you have in electric fields. There's another way of saying that probably makes more sense, at least when you start off. They store energy in a charge separation. A very key word there is separation. Capacitors separate charge between 2 locations, and the charge has to be placed close enough that it interacts to hold it there. The attraction between opposite charges holds it there. So this here shows pictures of actual capacitors you can find. You know, you have a ceramic here. You have a couple of them that are rolled. This one here is probably ceramic as well, and this is probably ceramic as well. Now it's probably ceramic, and this one's probably, these 3 here are probably rolled. So how do you make a capacitor? Making a capacitor is real simple. Really simple. All you need to do is have 2 plates that are separated. So this picture is your simplest, what we call parallel plate capacitor. You have 2 parallel plates. They're separated by some distance d, and they have some cross-sectional area A. That's all it takes to make a capacitor. 2 plates that are separated. Not very complicated at all. If you connect that to a battery, and Eddie Murphy's the one who taught me to say battery, okay? Just when I was in college, his album Delirious came out. You know, say, man, someone stole your battery. Made me say battery ever since. A battery is a battery of cells, of voltaic cells. If you look in your, well, what you put in your calculator is not a battery. You put a cell in your battery. But if you put a bunch of cells in, taken together, it's a battery. And if you have like an electric vehicle, if you take its battery apart, you see that it's just made up of a whole bunch of little cells, like your cells you put in your calculator, pretty much. So you connect it to the battery, and should time last long enough, we'll talk about the battery today. A battery is basically a charge pump. It gives energy to charge. And so it has a positive terminal and negative terminal and a voltage difference between those two. So if you connect those plates up, the positive terminal is going to attract electrons or remove electrons from the plate it's attached to. So the plate that is attached to the positive terminal becomes positively charged. But batteries do not gobble up charge. They do not supply charge. They just give it energy and move it. And so all of the electrons that leave the positive plate get deposited on the negative plate. So under the standard application of a capacitor, you have plus Q on one plate and minus Q on the other. And we say this capacitor is now charged to a charge of Q. So when we talk about the charge on a capacitor, we're talking about the charge on one plate, or the charge that was moved from plate A to plate B. We're not talking about the difference in charge of the two plates, because that could be confusing. Since one's plus Q and one's minus Q, you might think, oh, wouldn't that be 2Q? No, we're talking about the amount of charge removed from one plate or added to the other. So if we move that charge, now we're going to have an electric field. What direction do electric field lines point? From blank to blank. Okay, they go, that was reverse. They go out of positive and into negative. So electric field lines are going to go like this. Going out of positive and into negative. So that's what the electric field lines are going to look like between the plates of the capacitor. Now, if you go outside, they're going to be doing things like this. But in between the plates, it's going to be a uniform electric field, and you can calculate the relationship between the electric field and the voltage difference. Delta V is equal to ED. V is equal to Ed. Well, there's more things you can determine. If you use Gauss's law, the last homework problem for Physics 252 students is doing this. If you use Gauss's law, you can actually determine that the electric field between the plates is equal to the charge on the plates divided by area times the permittivity of free space, epsilon zero permittivity of free space. So you have the electric field and you have the voltage. Put those in and I have the voltage difference is equal to QD. I think I did that right. And so the voltage difference between the plates has to do with the charge. If you have a bigger charge separation, you have a bigger voltage difference. Now for the final thing on this, capacitance is defined as, well, here's how I remember it. The charge is voltage times capacitance. So capacitance is defined as the charge divided by the voltage difference. And so taking the two equations that I just made, I can substitute and say that's equal to Q over QD over A epsilon zero. So capacitance is equal to epsilon zero times A over the separation. I got to make that neater. So that's the equation to calculate the physical capacitance. I make two plates, I separate them by distance d. If they're parallel plates, the capacitance is a very simple calculation. And you know what? Even though in real life they're never parallel plates, for you guys, they're always going to be parallel plates. So that's the equation you're learning. In real life, of course, it gets more complicated because they use much more sophisticated geometries, such as this here. Here it's rolled up. Well, then your plates are effectively, both sides are participating in capacitance. And so you're doubling the area of the plates because both sides are participating instead of just one side. With ones like these ceramics, they use patterns that are like this, with there's one plate. And of course, these are not touching. And here's the other plate. And they can make these things so they're really, really close together. If you make them close together, what's that doing to the capacitance? If D gets smaller, C goes higher. And you have a lot of area because of the way they're packing in there. So if area goes up, C goes up. So by making them with these sophisticated patterns, they're able to raise the capacitance to the volume, to the size of it. So this is the physical structure. Their whole point is to store energy. So yes, this is what I just did. I can skip past it now. One thing we can do to improve the capacitance even more is to put a dielectric in there. What is a dielectric? We've already talked about dielectrics. Dielectrics are things that have electric dipole moments. That is, they're things that will have a positive negative charge separation. An example of a dielectric was water. The water molecule has, the H's have a net positive charge, the O has a net negative. It's a dielectric. We don't use water as the dielectric in capacitors. Why would the dielectric make a difference? If you put a dielectric between the plates, all those little electric dipoles are going to align so that the negative is attracted to positive, positive is attracted to negative. They align opposite to what the plates are. And by so doing, they're going to lower the electric field in the region where you have that electric dipole. So if you look at electric field, you still have the same charge on the plates. And so you're still going to have the same electric field here, but then you have a weaker electric field in the dipole. Or not in the dipole, in the dielectric. And so what it does when you put that dielectric in there is it allows you to create a bigger capacitance. And so it turns out that your emissivity becomes the emissivity of free space multiplied by a dielectric constant, which tells you how much the dielectric can create a reverse electric field. It tells you how effective the dipole is. So by putting this insulator, this dielectric between the plates, you can raise the capacitance even further. So there's one reason to use a dielectric in your capacitor. You go back to this capacitor and you insert a dielectric, and it will raise the capacitance. It will raise the amount of charge per volume that you, or volume, per voltage you put across it. Now here's a table of dielectrics. So vacuum has a dielectric strength, or dielectric constant, of 1. That is, it's vacuum, and epsilon 0 was in vacuum. Air is so similar to vacuum that we generally don't differentiate air from vacuum. There is a difference, but not very much. Paraffined paper, wax paper in other words. If you just put wax paper between your plates, you will make it so you have about twice the capacitance, between 2 and 4 times the capacitance. Teflon, 2 times, rubber, 3 to 4 times, paper, 3 times. Mica, 4.5 to 8 times. Mica is used a lot of the time in capacitors as the dielectric because you can get a big increase in capacitance. But there's another thing here, the dielectric strength, which I accidentally said the wrong time. Remember to our first lab, one of the groups was to measure the voltage of the Van de Graaff generator. How did they do that? No, they didn't use a voltmeter. Okay, I'm going with Corso because I heard it. I think you already said it. Okay, they measured the distance for the longest arc they could get. The dielectric strength tells you the maximum voltage per millimeter. Units of voltage per meter is units of electric field. So it tells you the maximum electric field that can be supported in that dielectric. If you make an electric field stronger than that, you can have charge pass through it. So the dielectric strength is telling you how good it is as an insulator. The higher the dielectric strength, the better the insulating properties. And so in air, it has a dielectric strength of 3,000 volts per millimeter, or 30,000 volts per centimeter. So they measured that they could make an arc about 5 centimeters, which meant that they had 5 centimeters times 30 kilovolts per centimeter was 150 kilovolts. So that's what the dielectric strength is. Oh, shoot, I'm out of time. Well, the dielectric strength is not the same as dielectric constant. It tells you how good of an insulator it is. And vacuum is the best.